Welcome to the deep dive. Today we are plunging into, well, one of the really big challenges in AI right now.
Yeah, absolutely. We're talking about how models handle enormous sequences of data.
And I mean enormous, like millions of tokens long. It's a fascinating problem area.
It really is. And it's not just a technical thing, right? It fundamentally limits what these large models can do. Think about analyzing huge documents or high-res video.
Or even complex sets of images.
Exactly.
And the material we're digging into today, it offers a really interesting, maybe even counterintuitive solution. We're focused on a research paper introducing something called LaGLIT.
That's large chunk test time training.
Right. So our mission today is really to unpack the academic core of LaGLIT. What are the key innovations? What makes it different?
Precisely. Think of this as your guide to the academic thinking behind it, the novel ideas that make it work.
Okay, so let's set the scene properly. Before AgLIT, what's the fundamental issue with long context? Why do models like the transformer, which are usually so good, why do they struggle when the data sequence gets really, really long?
It boils down to the attention mechanism itself. Standard attention, the kind that made transformers famous, well, its computational cost, and memory cost too, it scales quadratically with the sequence length.
Ah, the n squared problem.
Exactly. So if you double the length, you quadruple the cost. For, hundreds of thousands or millions of tokens, it just becomes computationally infeasible. Forget it.
It's that classic wall everyone hits. So people have tried different things. One interesting avenue mentioned is test time training, or TTT. What's the academic thinking there?
So TTT is kind of trying to bring back some ideas from older recurrent networks, like RNNs, but in a more modern context. The idea is to use a small subnetwork.
Okay.
And this subnetwork has fast weights. They're not fixed like the main model weights. They actually adapt during processing, both at training and inference time,
How do they adapt?
using a self-supervised objective on the incoming data itself. So the idea is these fast weights learn dynamically. They learn to store relevant information from the context they've seen so far.
Like a dynamic scratchpad memory?
That's a great way to put it. A memory that evolves as the model sees more data.
Okay, clever idea. But even TTT in its earlier forms ran into problems when people tried to scale it up to really long sequences, didn't it?
Oh, absolutely. The source paper points to a major blocker, both academic and practical. Hardware inefficiency.
How so?
Well, these earlier TTT methods, they often updated those fast weights based on really small chunks of data, sometimes just one token at a time, or maybe tiny batches like 16 or 64 tokens.
Right. And why is that bad for, say, a modern GPU? What's the academic reasoning?
It's all about parallelism. GPUs are designed for massive parallel computation on large chunks of data. You feed them these tiny little update tasks.
They don't have enough work to do.
Exactly. You're not giving them enough calculations per batch to really saturate all those parallel cores. The source even mentions utilization could drop below 5% sometimes.
Wow, okay, so most of the expensive hardware is just sitting there waiting.
Pretty much. And the worst part, academically speaking, is that to even get that tiny bit of performance, researchers had to write these really complex, very hardware-specific custom compute kernels.
Which sounds like a nightmare for research.
It is. It slows everything down. You can't iterate quickly. You can't easily try new architectures for those fast weights. It really hinders exploration.
Okay, so we've got the quadratic scaling of attention and then this hardware inefficiency bottleneck with the small batch TTT approach. That really sets the stage for XET's core academic innovation. This is where it gets good. What's the big shift?
Right, here's the pivot. And like you said, it feels counterintuitive when you first hear it. Instead of tiny batches, XET says use extremely large chunk sizes for updating those fast weights.
Extremely large. Like how large are we talking?
The paper mentions experiments using chunks, ranging from 2048 tokens all the way up to 1 million tokens in a single chunk for certain updates.
A million tokens. Wait a minute, doesn't updating on such massive chunks completely miss the point of TTT? Like, don't you lose that fine-grained step-by-step context building?
That's the immediate reaction, right? But here's the academic insight. It directly tackles the hardware inefficiency problem head on.
How?
By processing these massive chunks for each update, you dramatically increase the amount of computation performed per update step. You're giving the GPU a huge block of work, exactly what it's designed for.
Ah, okay, so you're making the update operation itself efficient by feeding the hardware what it likes, big chunks of parallelizable work.
Precisely. You amortize the overhead of launching the update operation over a much larger amount of data. The source has figures like figure 1a showing huge gains in GPU utilization and throughput compared to the old TTT methods.
So it's about matching the computation to the hardware strengths.
Yes. And the really crucial academic consequence of this is that you can achieve this efficiency using standard libraries, like native PyTorch. You don't need those custom low-level kernels anymore.
Which is huge for researchers.
It's massive. It makes this kind of advanced, long-context research much more accessible. The paper calls it democratizing the design space.
Okay, so democratizing the design space, making it easier to implement. And this hardware efficiency gain from large chunks, it must have knock-on effects. Does it allow for changes to the fast weights themselves?
Yes, that's the major payoff, academically speaking. Because you're no longer fighting this extreme hardware inefficiency, you can actually afford to make the fast weight network itself much larger and more complex.
Ah, you have the computational budget now.
Exactly. Remember those old TTT methods were stuck with tiny fast weights, maybe 0.1% to 5% of the main model's parameters.
Yeah.
LaCT pushes this way up. The source shows experiments scaling the fast weights up to 40% of the total model parameters.
40%. That's a huge part of the model dedicated just to this dynamic memory. And you mentioned complexity. Does it allow for different types of fast weight networks?
Yes, critically, it allows for nonlinear fast weight networks. They use things like the Swiggle UMLP architecture.
And why is nonlinear important here? What's the academic significance?
A larger nonlinear network just has vastly more capacity to learn complex functions. It means the memory component, the fast weights, can learn to store and utilize much richer, more intricate information from the context compared to simpler linear versions.
So the efficiency gain directly enables a more powerful, more expressive memory system within the model.
That's the core idea. And the results back it up. Figures like 1B, 1C, and 7A in the paper show that as you increase the fast weight size using XCT, the model's performance improves, especially on longer sequences. It's using computational efficiency to unlock better state capacity.
But ACT isn't only this large chunk TTT layer, is it? The paper calls it a hybrid architecture. What else is going on inside an ACT block?
That's a really important point. It's not just TTT in isolation. A typical ACT block, as described, actually has three main layers.
Okay, what are they?
You've got window attention, then the large chunk TTT layer we've been discussing, and then a standard feed-forward network like you see in transformers.
Okay, window attention. Why mix that in? Doesn't the TT layer handle the long-range stuff?
It does handle the long-range dependencies, yes, but remember, it processes updates over these very large chunks. Because of that, it might sort of gloss over the really fine-grained order or the spatial locality within that big chunk.
Like the exact order of words right next to each other, or adjacent pixels in an image.
Exactly that. And for most data text, images, video, that local structure is incredibly important. You can't just ignore it.
So the window attention handles the local details.
Precisely. Window attention performs self-attention, but only within smaller local windows. It's very efficient at capturing that interchunk structure and locality.
I see. So it's like a division of labor.
A very clever division of labor, academically speaking. Window attention takes care of the local neighborhood efficiently, and that frees up the TTT layer with its fixed size fast weight budget to focus all its capacity on modeling the really hard part, the non-local long-range dependencies across the entire sequence.
Interesting. The paper also talks about flexibility and how LaCT handles the update and apply steps for the fast weights. This sounds different from typical state-based models. Can you unpack that academic flexibility?
Yeah, this is another neat aspect. In many traditional stateful model, like an RNN, you process input, you update the state, you move to the next input, update state, and so on. It's very sequential.
Right.
LaCT decouples things. There's the update operation where the fast weights learn from the data in a chunk, and there's the apply operation where those learned fast weights are used to actually process queries or generate output for a chunk.
And these can be done in different orders?
Yes, and across different chunks, this decoupling allows for different processing strategies. The source highlights this in Figure 3, quite an interesting academic point. By changing the order of update and apply, LaCT can effectively mimic different kinds of attention masks, computationally speaking.
How so? What kind of masks?
Well, for instance, if you consider the whole sequence as one chunk, doing apply, then update is conceptually similar to full attention.
Okay.
If you process chunks sequentially and do update then apply within each, you get something like a block-wise causal mask looking back at previous blocks.
Makes sense.
But crucially, for something like language modeling, you need strict causality even within the current chunk. XCT achieves this by doing apply then update for each chunk. This creates a shifted block-wise causal mask, ensuring you don't accidentally use information from future tokens within the current chunk when generating the output for that chunk.
That's subtle but important for causality. What about only updating on some chunks?
Right, they show you can update on, say, every other chunk, but still apply the learned weights to all chunks. That creates a kind of strided mask pattern.
So this architectural flexibility lets it adapt its processing pattern based on the task.
Exactly. It can tailor how it uses its state to the specific causal or structural needs of different data types, like text versus maybe image sets. That's a significant innovation for a state-based model.
You mentioned earlier that these large chunks mean more computation happens during each update step. Does that open the door to using more sophisticated ways to actually calculate the fast weight updates beyond just basic gradient descent?
Yes, absolutely. Since the updates are less frequent but operate on more data, you have a bit more computational headroom per update.
So you can afford a more complex update rule.
Potentially, yes. The paper explores this. They test simple gradient descent, just standard SGD with L2 normalization, which works quite well, but they also experiment with a more complex nonlinear update rule they call Muon.
Muon. What's the academic motivation for trying something like that?
The goal is generally to improve the stability and maybe the effectiveness of how the fast weights learn and store information. While simple gradient descent is often sufficient, the paper suggests that rules like Muon might offer advantages, perhaps leading to a more robust learned state.
Does it make a big difference in practice?
The results are a bit mixed. Table 3 shows Muon has slightly lower training throughput, which makes sense as it's more complex. But other results, like Figure 8b for language modeling, suggest it can outperform linear updates in terms of final performance. It's really about exploring the design space that the large chunk approach opens up academically.
Now, for these methods to be truly practical, especially with giant models and sequences, they need to scale efficiently across multiple processors or GPUs. Is XET built with parallelism in mind?
Yes, that's crucial, and the paper addresses it directly. They discuss how XET is compatible with standard parallelism techniques, specifically context parallelism, CP, and tensor parallelism first.
Okay, context parallelism first. How does that fit with XET's structure?
With CP, you take a large chunk of the sequence and you shard the data within that chunk across multiple devices, say multiple GPUs.
So each GPU gets a piece of the chunk.
Right. Then operations that are local to the sequence elements, like the feed-forward layers or the window attention, can run in parallel on each GPU using its local shard of data.
But what about the TTT update? Doesn't that need infos from the whole chunk?
It does mathematically. So for the fast weight update step, which involves aggregating gradients or other information across the entire chunk, they use standard distributed communication options, like an all-reduced sum, to efficiently combine the results from all the devices working on that chunk.
Got it. And tensor parallelism. How does that work here?
TP is about sharding the model parameters themselves. In LaCT's case, they specifically talk about sharding the TTT heads across devices.
Sharding the memory part.
Yeah, essentially, each device might get the full chunk sequence data, but it's only responsible for computing the updates and applications for a subset of the TTT heads. This involves some data gathering and scattering, but allows scaling the fast weight computations themselves.
So you can divide the work by sequence position using CP and by the model's memory heads using TP.
That's the basic idea. And the paper provides details, often in the appendix, showing this was necessary to run their biggest experiments, like a 14 billion parameter video model on sequences over 100,000 tokens. This built-in scalability is a key part of its practical academic innovation.
Okay, so the architecture is designed for scale. How did they actually validate that FCT works well? The paper covers tests across quite different types of data, right?
Yes, and that's really important for showing the generality of the academic framework. They tested it on 3 distinct tasks, which really probe different aspects of sequence modeling.
What were they?
First, novel view synthesis, which uses sets of images. Second, standard language modeling on text. And third, auto-regressive video diffusion, which deals with sequences of images, basically video frames. Table 1 summarizes the setup for each.
Okay, let's take novel view synthesis. How did LaCT perform there?
Here, the idea was to feed the model a set of input views of an object or scene, let it compress that information into its fast weights, that's the prefill stage, and then use that learned state to render new, unseen views.
And the results?
The results, shown in Table 2 and Figure 4, were strong. LaCT achieved rendering quality comparable to models using full attention, which is impressive. But crucially, its prefill stage, where it learns the state, was significantly faster than full attention.
Faster than full attention, same quality. How about compared to other efficient methods?
It substantially outperformed other linear cost approaches, like perceivers, in both the speed of prefill and the final rendering quality. So a clear academic win in that domain.
All right, what about language modeling? That's a classic benchmark.
For text, they used causal modeling, applying that shifted blockwise mask we talked about, along with sliding window attention for local context. Figure 5 shows the model effectively leverages context over really long sequences. The loss keeps going down as it sees more text. which is what you want.
And on specific benchmarks.
They tested it on the ruler benchmark, which is specifically designed to measure long-range dependency and retrieval capabilities in language models. The results there, in tables 8 and 9, show LaCT being competitive with, or often superior to, other ending linear cost baselines like DeltaNet and GLA. And notably, it performed particularly well when using those larger, nonlinear fast weights we discussed.
Okay, strong showing there too. And the final test case, auto-regressive video diffusion.
Yeah, this one really pushes sequence length. They were dealing with sequences of over 100,000 visual tokens representing video frames. The task was to generate video by denoising chunks based on past context stored in the fast weights.
And how did it fare?
Figure 6 shows ACT achieving validation loss very close to a full attention baseline, which is remarkable given the sequence length. And importantly, it significantly outperformed other efficient baselines like Mamba 2 and a standard sliding window attention approach. This demonstrates its academic potential for really challenging, long-sequence generative tasks like video.
Now, like any research, especially cutting-edge stuff, the paper is also upfront about current limitations. Where does XCT still have room for, let's say, academic growth or future work?
Yeah, they point out a few things. One specific technical point is that the fast-weight components they used, like SWIGO-U and linear layers, don't inherently have rotation invariance.
Rotation and various. Why does that matter?
Well, it's a property that standard attention and some linear attention variance naturally possess, and it can be useful, for example, when implementing relative positional encodings. They note its practical impact in ACT isn't fully explored yet, so it's an area for potential refinement.
Okay, a potential property to add later. What else?
They also mention limitations related to scale and task scope, mostly due to computational budget constraints common in academic research. While they validate it across diverse tasks, they suggest that pushing parameter counts even higher or evaluating on more complex reasoning benchmarks for language models would be valuable future work.
Exploring the absolute limits of its reasoning capacity.
Exactly. And similarly for video generation, they acknowledge that robustly evaluating the scalability of any video generation model is still a general academic challenge. So while their results are promising, demonstrating ACT's full potential at massive video scale needs more investigation as evaluation methods improve.
That makes sense. So, thinking about these limitations, for you, the listener who's maybe exploring this academic space, how might these current boundaries influence where you'd see ACT being most effectively applied right now versus areas where maybe more research is needed first? It's something to consider. So, let's try and wrap this up. What's the big picture takeaway here? ACT really seems like a compelling new academic angle on the long context problem.
I think so. By making that really bold, counterintuitive move to large chunk updates for test time training, it offers a genuinely novel academic solution to the hardware efficiency bottleneck that plagued earlier TTT methods,
Right, and that efficiency isn't just about speed, it's the key that unlocks the ability to use much larger, much more powerful, nonlinear fast weights.
which significantly boosts the model's capacity to actually remember and use long-range context effectively. It gives it a much better dynamic memory.
And then combining that powerful TTT layer with local window attention creates this elegant hybrid architecture. It's flexible, it divides the labor effectively.
And crucially, it works. The validation across image sets, text, and long sequence video shows strong results, often matching or beating other methods.
And the fact that it can be implemented efficiently in standard frameworks like PyTorch without needing crazy custom code is a huge practical advantage for the academic community.
Definitely. It represents a really significant academic step forward in how we design efficient sequence models that have this kind of stateful dynamic memory component.
So here's a final thought for you to mull over. If the core academic innovation here is really about finding a clever way to use our existing hardware much more efficiently, specifically to enable a more powerful memory component within the AI, what other really complex, long sequence problems might this kind of approach unlock? Maybe problems outside the usual vision and language domains? What new research directions or creative applications could this more democratized access to efficient long context modeling spark next?